Quantum entanglement is a strange and mysterious phenomenon that has fascinated scientists for over a century. The basic idea is that two quantum particles can become entangled, meaning that their properties become correlated in such a way that they can no longer be described independently of each other. This means that if something happens to one particle, it will affect the other particle instantaneously, no matter how far apart they are. Einstein referred to this as spooky action at a distance. The concept of quantum entanglement was first introduced by Albert Einstein, Boris Podolsky, and Nathan Rosen in 1935. They published a paper in which they argued that quantum mechanics was incomplete because it could not fully explain the behavior of entangled particles. However, it wasn't until the 1960s that physicist John Bell showed that the predictions of quantum mechanics regarding entangled particles were correct, and that Einstein's objections were wrong. One of the most famous examples of quantum entanglement is the Einstein-Podolsky-Rosen (EPR) paradox. This thought experiment considers two particles that are entangled and then separated. According to quantum mechanics, the state of each particle can be described by a wave function. When the particles are entangled, the wave functions of the two particles become correlated, and it is no longer possible to describe the state of each particle independently. So, if something happens to one particle, it will affect the other particle instantaneously, no matter how far apart they are. This was the spooky action at a distance that Einstein was talking about. Entanglement has a number of practical applications, such as quantum computing, quantum key distribution, quantum metrology, quantum teleportation, and quantum simulators. Quantum computing is a new way of performing calculations that makes use of the properties of quantum mechanics. Unlike classical computers, which use bits, zeros and ones, to represent information, quantum computers use quantum bits or qubits. These qubits can exist in a superposition of states, meaning that they can represent multiple states at the same time. This allows quantum computers to perform certain calculations much faster than classical computers. One of the most famous examples of quantum computing is the factoring of large numbers. A classical computer would take an impractically long time to factor a large number, while a quantum computer could perform the task in a fraction of the time. This could have huge implications for encryption, as it would make current encryption methods obsolete. Another example of quantum computing in action is Google's quantum computer, which in 2019 performed a calculation in 200 seconds that would have taken the world's fastest classical computer 10,000 years to complete. Quantum key distribution is a method of creating unbreakable encryption using the principles of entanglement. One example of this in action is the Chinese satellite Mishus, which was launched in 2016. It uses quantum key distribution to establish a secure link between ground stations and the satellite, allowing for the transmission of ultra-secure keys for encoding and decoding data. Entanglement has been proposed as a way to improve the precision of measurements in quantum metrology. By using entangled particles, it is possible to achieve a higher precision than what is possible with classical measurement. For example, in a process called quantum illumination, entangled photons can be used to detect the presence of an object in a noisy background. The advantage of using entanglement is that it allows for a higher signal-to-noise ratio, making it possible to detect the object with a higher precision. Quantum entanglement has also been proposed as a resource for quantum communication. By using entangled particles, it is possible to transmit information in a way that is secure from eavesdropping. This is due to the fact that any attempt to measure the state of an entangled particle will disturb the state of the other particle, making it possible to detect any attempt at eavesdropping. In recent years, there has been a growing interest in using entanglement for quantum computing. Quantum computers have the potential to solve problems that are intractable for classical computers. One of the key features of quantum computing is the ability to perform certain operations on a quantum state that are not possible with classical states. For example, a quantum computer can perform a quantum Fourier transform, which is a key operation in many quantum algorithms in a much faster time than a classical computer. One of the main challenges in building a practical quantum computer is the ability to control and manipulate the quantum state of the qubits. One way to overcome this challenge is to use entanglement as a resource. By using entanglement, it is possible to perform operations on a quantum state that would not be possible without it. For example, by using entanglement, it is possible to perform a quantum teleportation, which allows for the transfer of a quantum state from one qubit to another without the need to physically transport the qubit. Entanglement is also related to the concept of wormholes and teleportation. Wormholes are shortcuts through space-time that could allow for faster than light travel. In theory, it is possible to use entanglement to create a wormhole, which would allow for instant communication between 2 points in space-time. Similarly, it is possible to use entanglement to achieve teleportation, which would allow for the transfer of matter or information from one point in space to another without the need for physical transport. However, despite all the potential benefits and applications, there are still debates and controversies regarding the reality of quantum entanglement. Some argue that entanglement is simply a mathematical artifact and not a physical phenomenon, while others argue that it is a real physical phenomenon that can be harnessed for practical applications. In terms of commercial use, there are already a few products that utilize entanglement. For example, companies such as ID Quantique and Quintessence Labs have developed entanglement-based quantum key distribution systems for securing communication network. Additionally, companies such as EON-K and Rigetti Computing are currently developing and selling quantum computers that utilize entanglement. In conclusion, quantum entanglement is a fascinating phenomenon that has the potential to revolutionize the way we think about physics and technology. The ability to harness entanglement for quantum computing and communication could lead to breakthroughs in fields such as cryptography, simulation, and sensing. However, the true nature of entanglement and its relationship to other quantum phenomena such as wormholes and teleportation is still a topic of ongoing research and debate. Ultimately, it is clear that the study of entanglement will continue to push the boundaries of our understanding of the universe and open new doors for technological advancement. Some of the products that are in commercial use that are based on this principle are quantum key distribution and quantum random number generators. We hope this video has been informative and has sparked your interest in the world of quantum mechanics. Don't forget to subscribe to our channel to stay updated on the latest developments in this field.